In the last video, we introduced row operations, which were things that you could do to the rows of a matrix, which correspond to the kind of manipulations that we make to systems of linear equations when we're trying to solve them. It's going to turn out that doing a row operation to a matrix is in fact equivalent to multiplying that matrix on the left by another matrix. Those matrices are going to be called elementary matrices, and they're the first definition here. So an elementary matrix is defined to be a matrix which is obtained by doing a single row operation to an identity matrix. So here I've got the 3 by 3 identity, and let's see 3 elementary matrices which we can obtain by doing an example of each of the 3 different types of row operations to this identity matrix. So let's do the row operation which sends row 3 to row 3 minus row 1. Okay, where would that send us? We would end up with row 1 won't change, row 2 won't change, and the only thing that will change is row 3, which becomes minus 1, 0, 1. So that thing which I've just written down is an example of an elementary matrix. Let's see some more. So if I take the row operation which sends row 2 to 2, row 2, then we get an elementary matrix where row 1 didn't change, row 3 didn't change, but in row 2 we got 0, 2, 0. So there is our second example of an elementary matrix. And our final example, we'll do a row swap. So let's say we do the row operation which swaps row 1 and row 3. And if I did that, then this matrix will go to a matrix where row 2 didn't change, and row 3 became row 1, and row 1 became row 3. So those are 3 examples of elementary matrices. Now, what we're now going to show is that if you do a row operation R to a matrix A, then the result, so R of A, is the same as left multiplying A by the corresponding elementary matrix. So R of A, doing the row operation R to A, is the same as left multiplying A by the elementary matrix R of the identity. So why is this true? Let's think about why this is true. In fact, what we'll do is we'll prove something a little bit more general. So we're going to take any m by m matrix X. And I'm going to give some names to the rows of X. So I'm going to call the first row of X R1 as usual, and the second row R2, and so on. So the last row will be Rm. Now let's think about what happens when we do a particular row operation to this matrix X. So we're just going to think about one specific example of row operation. The other row operations can be done in a very similar way. So suppose that R is the row operation which adds lambda times row j to row I. Okay, so our row operation R will add, will change row I, and it will add lambda times row j to row I. So then we can say what the matrix R of X looks like. R of X, where all the rows are the same, and the only row that changes is row number I. So I'm just going to not write anything except in row I, which is changed because row I is now row I plus lambda times row j. Okay, all the other rows of X are the same. All the other rows in R of X are the same as the corresponding rows in X, except row I has changed and is now row I plus lambda times row j. Okay, so let's look now at X with this row operation R applied to it, then multiplied into A. So what can we say when we do this when we do this matrix multiplication? Well, we know about how matrix multiplication can be thought of row-wise. So R of x times A would be, its first row would just be R1 multiplied into A. And its second row would be R2 multiplied into A, and so on. And the last row would be Rm multiplied into A. Okay, and the only bit where x times A would differ from R of x times A would be in row I, which would be Ri plus lambda Rj times A. Okay, so that's what the rows of R of x times A look like. The first row is R1 times A, the second row is R2 times A, and the ith row is Ri plus lambda Rj times A. Okay, so let's now think about what happens when we do x times A. So again, x times A, we can think about doing this multiplication row by row, and when we do this row by row, we get R1 times A, R2 times A, and so on, all the way down to Rm times A. Okay, so what about R of xa? So remember, our row operation R only changes the ith row, and it adds lambda times the jth row to the ith row. So what would I have? The first row, I just have R1A again, and on my last row I would have Rma, and the only place where something interesting happens is when we have row I, which would be the ith row, which is Ria plus lambda times the jth row, which is Rja. Okay, so that's what we've got here. But if you look at this row here of R of x times A, well, you could multiply out that matrix multiplication which is happening in row I, and you get Ria plus lambda Rja, which is the same as this. So those things are equal. Because R, the ith row plus lambda times the jth row, all multiplied into A by our matrix multiplication properties, is the same as Ri multiplied into A plus lambda times Rj multiplied into A. Okay, so what have we got there? We have R of xa equals R of x times A. Right, and remember, this worked for any matrix A and any m by m matrix X. So if we just take X to be the identity, then what you would get by taking X to be the identity is just that R of, well, in brackets we'd have X times A. X is the identity, so we've got the identity times A, so that's just A again, and that's R of the identity times A. Okay, so that was what we wanted in the specific case of the first type of row operation. Now, all of the other types of row operations can be done in exactly the same way, and so you can prove this theorem just by checking the other two cases. If you want to see it done in a actually slightly different way, then you can look at section 3.8 of the notes. But that gives us our nice result about, well, a nice result that says doing a row operation is the same as left multiplying by the corresponding elementary matrix. And we can get something else out of this, which is that every elementary matrix is in fact an invertible matrix. So the reason this is true is that you know that every row operation is invertible. So if R is a row operation, so row op for short, then there is an inverse row operation. So remember, we saw a table telling you for each row operation what its inverse was in the previous video. And the meaning of inverse here was that for any matrix A, R of R inverse of A, and of course R inverse of R of A was just A again. So you got back to where you started if you did the row up and then you did the inverse row up. Okay, well, let's think about the theorem at the bottom here, which was the theorem from the previous slide. It said that doing a row up was the same as left multiplying by the corresponding elementary matrix. So let's just think about what happens if we do our row operations to the identity matrix. So if I have the identity matrix, let's say the m by m identity, that's the same as doing r to r to the minus 1 of the identity. That's just because r and r inverse are inverses of one another. Okay, now what does theorem 3.8.1 tell us about doing r to this matrix r to the minus 1 of I? It tells us that that's the same as left multiplying by r of the identity. So here, let's put the m in there. So what we've got here is r of im times r inverse of im. So this is by theorem 3.8.1, the one from the previous slide. Okay, and similarly, because doing r inverse gets you back to where you started, we would get that r inverse of the identity times r of the identity is the identity. Okay, so we've shown that the elementary matrix R of the identity is invertible and its inverse is R inverse of the identity.